The next sorting algorithm that we need to understand and implement is quick sorting algorithm. So quick sorting algorithm, also the entire principle behind the quick sorting algorithm is divide and conquer only. That basically means that we will try to divide the array into two parts such that we can sort those individual parts of the array such that in the end we will basically get the entire array sorted. So the principle is just divide and conquer, just like what we had in the case of merge sorting as well. In the case of merge sorting algorithm, we divided the array and applied the same logic on the left part of the array and on the right part of the array based on the middle index that we are getting. Basically, we are dividing the entire array into two halves, okay, in the case of merge sorting algorithm. But in the case of quick sorting algorithm, the division of array into two parts depends upon the pivot index calculation that we have discussed previously. Once we get the pivot index, we will basically apply the same quick sorting logic on the left part of the array. That means whatever the values that we have on the left side from the pivot index, and we will apply the same quick sorting algorithm on the right side of the pivot index as well. As a result, in each and every step we will pick up a particular element and we will move it into its perfect position. As a result, in the end we will basically get the entire array sorted. Okay, and one more important thing that you have to remember here is quick sorting algorithm is one of the in place sorting algorithm only. Just like what we had in the case of bubble sorting, selection sorting and insertion sorting, quick sorting is also one of the in place sorting algorithm only. In the end, that basically means that whatever the input array that we get, right, in that same input array, in the end we will get the resulting sorted array as well. Okay, so let's just try to understand the same thing on an array of values that we have here, and let's just try to sort it in the ascending order using the quick sorting algorithm. So here the values that we have got are 1, 4, -5, 3, 7 and -2 and -10 is the are the values that we have got in the input array. Let's just say we have got these values in the input array A. As I mentioned previously, quick sorting is going to follow divide and conquer based approach, right? That means on the left part of the array we will replicate the same logic, and on the right part of the array we will replicate the same logic. That basically means that we will simply solve this sorting using the recursive approach. In the recursive approach, basically we will pick up a value and we will move it to its perfect position, right? Once we move it to its perfect position, later on we don't move that value to any other specific position, because once we move that value to its perfect position, it itself is the final position for that specific value. As a result, in the quick sorting implementation, what we will do is we will basically take the start index and end index in the array of values that we are getting. Since it is an in-place sorting algorithm, we will pass the entire array for implementation along with this start index and end index, and we only worry about applying whatever the logic that we are going to discuss. We will apply only in this range only. That means that when I call the quick sorting algorithm in the beginning, the start index will be 0 and end index is nothing but the very last index we have in the array. Here on the array of values we got, the last index is 6. Okay, now what we will do as part of the first step, we will try to find the pivot index such that we can divide the array into two parts and we can reapply the same logic. So if we apply the pivot index on this array that we have got, right, in the previous step we have already discussed this. The resulting array is -10, -5, -2, 1 and 7, 4, 3. Okay, if you remember, as part of the pivot index, what we will do, first we will pick up the value that is at the start index that we are getting. In that, specifically we will try to move the value at the start index to its appropriate position till whatever the end index that we are getting. So once we move this value 1 to its perfect position, 1 will be moved to index 3. Now what we can do, we can simply reapply the same quick sorting logic on the left part of the array and on the right part of the array. For left part of the array, the starting index will be 0 and ending index will be pivot index -1. So here pivot index is 3, right? So for the next recursive call, the pivot index will be 2. And for the right part of the array to be sorted, the starting index will be pivot index plus 1. So 4, and ending index will be the last index that we have in the array, which is nothing but whatever the end index we get. Here end index is nothing but 6, right? That is the one. Now what we will do, we will again apply the quick sorting algorithm on this left part of the array by passing the entire array, and the start index for this will be 0 to 2, and we will call the same quick sorting algorithm on this right part of the array. For this, starting index is 4 and end index is 6. That recursive function will again get called internally by picking up the starting element and moving that specific value to its appropriate position. As a result, in the same input array whatever we have, we will basically get the entire array sorted. Okay, now I will not go into each and every recursive call, and I will not try to explain what is exactly going to happen as part of each and every recursive calls, pivot index calculation and all. But the only thing that you have to remember here is, let's just try to put it into simple steps, and after that let's just try to write the pseudocode. As part of the quick sorting algorithm, we will pass the entire array in each and every step along with the starting index and ending index that we need to search in that specific range. Once we have that, inside this immediately we will calculate the pivot index. Once we get the pivot index, we need to call the same recursive function on the left part of the array and on the right part of the array. For left part of the array, what we will do, let's just assume that we are writing a quick sorting by the function name QS, short name. So for left part of the array to be sorted, we will pass the entire array. For this, starting index will be whatever the starting index that we get, along with that ending index will be pivot index minus 1 for the left part of the array. For right part of the array to be sorted, we will call the same function recursively by passing the entire array. For the right part of the array, the starting index will be pivot index plus 1, end index will be whatever the end index that we get in the function call. Okay, so based on this recursive calls, in each and every step this pivot index calculation will happen. Based on that, again we will divide the array into two parts, and in the end we need to stop the execution, basically calling these recursive functions at a specific point, right? That specific point is nothing but once this start index becomes greater than or equal to the end index that we have. That basically means that we have sorted all the values. As a result, we can stop the recursive calls. That itself is a base condition for the recursive implementation that we are going to do. So those are the steps that we will be following for implementing the quick sorting algorithm in a recursive fashion. Based on the steps that we have discussed previously, let's just try to write the pseudocode for this quick sorting algorithm. So as part of this quick sorting algorithm, we will simply write one function called quick sorting. This will take the array of values along with the start index and also the end index, basically the range of values in which we need to perform the quick sorting once again. Okay, as we are going to implement this quick sorting algorithm recursively, right, we need to add a base condition which will basically stop adding further recursive calls into the stack, such that basically we are giving a proper termination point. As part of this quick sorting, basically we can assume that the entire array is sorted whenever the start index is becoming greater than or equal to the end index. As a result, as part of the base condition, what I will do is, if at all if the start is greater than or equal to end, I will simply return the whatever the array that we are getting itself. Okay, if this is not the case, what we need to do, first we need to divide the array into two parts, such that on the left part of the array we can call the same quick sorting algorithm, and on the right part of the array as well we can call the quick sorting algorithm. So that point where we divide the array into two parts is nothing but pivot index calculation. So we have already discussed and we have written the pseudocode for implementing the pivot index, right? So what I will do is, I will simply call this pivot function whatever we have written previously. I will pass the entire array, and I need to run that pivot index logic also in this start to end range only. That's the reason why, you know, I have passed whatever the start and end values that I'm getting as part of the quick sorting function call itself. As part of this pivot, what we will do, we will pick up the element that is at the start index and we will move that value to perfect position such that all the left side values will be smaller and all the right side values will be greater. And whatever that value we have moved to its perfect position, that is nothing but this pivot index. Now based on this pivot index, we can divide the array into left half and right part of the array. I mean, they need not be necessarily half, basically left part of the array and right part of the array. So to sort the left part of the array, what I will do is I will simply call the same function by passing the entire array. For this left part of the array, starting index will be whatever the starting index that we are getting, and end index will be this pivot index minus 1. So start will remain same for left part of the array and end will be this pivot index minus 1. Okay, so as a result, this quick sorting is getting called on left part of the array. Again, we will check if the start is becoming greater than or equal to end. If not, again in that part of the array we will calculate the pivot index, and if at all if we have some more values, we can divide the array into two parts. This function will again get called and the same recursive function calls will get executed till we reach a point where this start index is becoming greater than or equal to end. This is about the left part of the array. What about the right part of the array, right? For sorting the right part of the array, I will call the same function once again, quick sorting. I will pass the entire array. For the right part of the array, the starting index will be pivot index plus 1. So start value will be pivot index plus 1. End will be the last value, which is nothing but whatever the end index that we are getting. So we will pass end as a whatever the end that we are getting in the function call of the quick sorting. Okay, again this quick sorting also gets called in the similar way, right? So it will check if at all if the start is becoming greater than or equal to end. If not, immediately we will calculate the pivot index in the right part of the array, and whatever the right part of the array that we get, based on the pivot index that we get inside that part of the array, again we will divide that array into further left part and right part, and the same functions will get called till we reach a point this start index is becoming greater than or equal to end. Okay, if you see here, we are not consuming any additional memory like what we had in the case of merge sorting algorithm. In the case of merge sorting algorithm, in each and every step we were getting half of the array sorted such that we need to merge them. As a result, we were creating an array whose size is equal to sum of the two sorted arrays sizes that we are getting. As a result, in the worst case, we had to consume order of n units of space. But in the case of quick sorting algorithm, in the array, whatever we are getting, we are simply moving each and every value to its perfect position using this pivot logic. Based on that pivot index, we are dividing the array into two parts and we are solving the same function, sorting recursively. Okay, so that is the recursive way of implementing the quick sorting algorithm. Let's just quickly do the time complexity and space complexity analysis of this quick sorting implementation that we are doing. And this also, let's just try to analyze it in the best case and in the worst case scenario. Okay, obviously the best case scenario will basically occur whenever we are trying to sort the array with only one value. In that case, the time complexity and the space complexity both will remain constant, which basically will be represented as order of 1 as we know. Now let's just try to analyze what could be the worst case time complexity and space complexity in the quick sorting implementation. Let's just assume that whatever the array that we are getting, right, let's just assume that we have n number of values in the array. As part of the first step, we will basically try to find the pivot index, right? Out of all the n values we have, as part of the very first step, we need to move the value at the index 0 to its perfect position. As a result, we need to compare that basically with the remaining n minus 1 number of values we have in the array. As a result, this pivoting logic, whatever we have, will basically consume order of n units of time. But the thing is, in each and every step we are trying to divide the array into two parts, right? Basically left part and right part, and this division is basically happening for log n number of times, because in each and every step we are dividing the array into further parts. As a result, the number of times the logic basically gets repeated is log n number of times. As a result, in the worst case, the time complexity of this will be order of n log n. Now, to analyze the space complexity of this quick sorting algorithm is one of the in-place sorting algorithm only, right? That means whatever the input array that we are passing, in that same input array, we will get the, end sorted result. Okay, and if you look at the implementation that we are doing here also, the only variable that we are declaring is this pivot index, and this pivot index is anyway going to consume constant amount of memory only. As a result, in the worst case where we try to sort the array which has n number of values, the space complexity theoretically it is constant only, but as we implement this quick sorting recursively, right, whatever the function calls that we are making recursively, all these function calls will go and sit inside the call stack. As call stack is going to consume some amount of memory for storing those calls, right? As a result, as we are repeating this logic for log n number of times, the worst case space complexity will be order of log n. This log n is nothing but basically the amount of memory consumed by call stack, not the amount of memory that we are consuming in the variables that we are using in the implementation. So that is the difference that you have to notice here. But if you don't want to consider this call stack memory consumption, the quick sorting implementations space complexity in the worst case also constant only. Okay, so that is the quick sorting algorithms time and space complexity analysis.